Okay. All right, so central limit theorems. This is something I already covered actually. So this is the derivative notation, right? And the chain rule, product rule, and the mean value theorem. We just covered that in our last lecture. So I will skip that. I will go directly into this central limit theorem. So this is the result. All right, so we are giving you the vector form again, unlike the introductory course you might have taken, because in there you will just learn maybe the scalar form. But here, x1, x2, they are random vectors. They have mean mu and finite covariance matrix sigma. So for example, if you have x1, x2, IID, right? And they follow, I should say, if they're all RD, then the mu is RD, okay? And the covariance matrix sigma is actually D by D. So the dimensions should match. So the central limit theorem and this finite here is important, right? We cannot have infinite values in the covariance matrix. So this is the result. It's just what I said. So you take the difference between x bar and mu, and this is also RD, okay? And you scale it by square root of n. Then it converges to this d-dimensional normal distribution. So it's a multivariate Gaussian distribution with mean zero and covariance matrix sigma. How do we interpret this result? Why do we need to multiply root n on the top, on the left? Any ideas? So yeah, go ahead. Yeah, go ahead.
I thought it had something to do with the variance slash standard deviation. That would be my intuition.
Yeah, you have very good intuition. Exactly. So if we just give you this one scalar, the scalar form, right? This is something you have learned before. That is, if we have x1 to xn, just r, okay? And if we have expectation of xi being mu, and we have the variance of xi being sigma square finite. Okay, if this is the setting, then we know that expectation of x and bar average is mu, no problem. Variance of x and bar is what? It's sigma squared over n. This is what we would know, right? And this variance will go down to 0 as n goes to infinity. So if we know that x and bar will be more and more likely normally distributed, then we can write central limit theorem result approximately as normal distribution mean mu variance sigma squared over n. So if we write this way, then the problem with the right-hand side is that it will go down to 0. So this distribution itself will converge in law to a point mass at 0, right? Because you will actually have shrinking variance. The variance is shrinking down to 0. So you will just have a, point mass at mu. You will just have a point mass at mu. That's the problem. But what happens if you don't have this, if you just have this, not like this, right? So what we can do is that we can first write x and bar minus mu, put it on the left-hand side, and this will be approximately normal distribution mean 0, sigma squared over n. This is by the shifting. Oops. This is by the shifting property of a normal distribution. Okay, but the right-hand side is still going down to a point mass at 0, right? This problem is still not solved, but we can now apply the scaling. And you know the scaling doesn't change the center at 0. That's the nice thing, because we are now center at 0. So if we multiply root n to the left-hand side, then you see we stabilize the right-hand side. So now the right-hand side no longer changes. All the changes with our sample size happens on the left-hand side. Okay, so this is the scalar version of this. And now we're showing you the vector version. Okay, so the key thing, like Zui said, is that the variance of sample mean go down at the rate of 1 over m. But now if we look at the standard deviation, it go down at the rate of 1 over square root of m. So that's why we multiply the square root of n on the left-hand side. This is central limit theorem. And the proof can just be done by using that Levy's continuity theorem. This is what I said. So essentially, to prove it, you write down the characteristic function of the left-hand side. And to do that, we express xn bar as the sum of x1 to xn, right? So if we change it to the sum, from the average to the sum, then since we need to divide m by the sum to get the average, so 1 over m cancel with root n, and we get 1 over root n. And we just need to get the characteristic function. So we know some properties. For example, if you have random variable scaled, then the scale can enter the characteristic function argument into the t. And if you have the characteristic function of sum of independent variables, then you get a product of characteristic functions of each random variable. So essentially, you would just get the characteristic function for each xi here, and you have the root n goes into the t, and you scale, you raise to power m because you have multiplied this for n times for n sample size. So essentially, you have the characteristic function for xi minus mu, each copy, not the average. And the characteristic function have some nice properties, okay? For value at 1, that's 0, derivative at 0, second derivative at 0. So these cannot be shown. So the derivative of the characteristic function at 0 is just the mean. And the second derivative of the characteristic function at 0 is just negative covariance. So these are the nice properties we apply here. And we have Taylor theorem. So essentially, we're just expanding this around 0, because we know as n goes up, this value t over root n will get closer and closer to 0. So we expand it at 0, we do the Taylor theorem, and we get here, right? And finally, we're just applying this important result, which is this. I'll just quickly write it. It's just 1 plus n over 1 plus a over n raised to the power n. This will converge to exponential a. That's it. That's the result we're going to use. So essentially, you have this thing written as 1 plus something, and this term is going down in the order of 1 over n. 1 plus 1 over n times something. And here you need to raise it to power m. So this whole thing will raise to power m. And then we apply the limiting result as here to here. And then you would have this what? This is just the characteristic function of this normal distribution. And then you're done. So essentially, we're using the convergence of characteristic function point-wise for t to get central limit theorem. And this is the application of Levy's continuity theorem. Okay, so yeah, with this, actually, it's not that difficult. Basically, you apply Taylor theorem to get this 1 plus something over n term, and then you raise this whole term to the power n. Okay, and one thing we have to note here is that central limit theorem, as it stands, has this most important condition, IID. Okay, x1, x2, xn, they're all IIDs. What if your data is not exactly IID? Can we still have some variant of the central limit theorem? So that is what we hope to talk about in this class. So this will now gets beyond what we learned in the undergraduate class about central limit theorem. So we call them extension of CLT. So here, I'll just quickly show that I'll just say that the extension of CLT to the independent. So first extension is that we look at independent but not identically distributed case. Okay, because in some cases we may have our sample not identically distributed, but they're independent. So in this case, how can we have a variant of CLT? And for now, we will express this in the form of a triangular array, which will show you why. So, but basically, just to let you see this formulation is that, okay, we can consider a row as a sequence of IIDs. So basically, you can consider x1, 1 on its own, x2, 1, x2, 2 to be IID, x3, 1, x3, 2, x3, 3 as IID. So we can have within every row IID, and we can let the row grow indefinitely. So we can have an infinite number of rows to create a sequence. And let me see. This is the result we can get for that extension. So this is the most important result and which has been very widely used in deriving the asymptotic distribution of many statistics. So just going back to the central limit theorem, we basically say that this normal distribution here is the limiting theorem of this statistic. That's what we say. Okay, so in other words, if we want to derive any confidence interval, or in this case, confidence set, because mu is a vector of mu, we can use this limiting theorem. And we can also use this limiting theorem to convert xn bar, the test statistic value, the sample mean value, into a p-value if we use the hypothesis testing about mu. So these are all the uses for central limit theorem. So for extensions of central limit theorem, essentially here the xn bar may be the average of some complicated scenario. That is, we have independent but not identically distributed sample. Okay, all right, so let's look at this so-called Lindberg-Feller theorem. So essentially, as I said, now we consider the row n1, 2, and so on, the row to grow. And within the row, we have x and I. Okay, I from 1 to n. So that is what we just saw, right? We have x11, x21, x22, x31, x32, x33. I think you will have more intuition after we show you some examples of the application of Lindberg-Feller theorem. But for now, let's just bear with me to look at this statement of the theorem. And I'll try to explain what it means. Okay, so we have x and I, and n is the row index, and I is within the row index. So they are independent random variables, and they all have mean 0. Okay, we just make it simple for us, because for each random variable, we can shift its mean to 0. And variance, x and I, to be sigma ni squared. Okay, so essentially, we can even be more relaxed than what I said. Within the row, you can have even different variances. So each x and I has its own variance sigma and I. They may not be equal to each other, but we still have independence. Okay, so now Zn is the sum. It's the sum of the row. Okay, so in this case, we have Z1, Z2, Z3. So every row, we get a row sum. And for each row sum, we get its own variance. And we know this is just sum of the within row variances, right? So basically we have the variance as B1 square, B2 square, and B3 square. So essentially, let me say here, what we have in the setting is that each Zi in the ith row, or let's just use a Zn. Zn in the nth row is row sum is 0, has mean 0. The variance of Zn, we denote as Bn squared. Okay, that's what we have the setting. And by this setting, essentially, all these Zn's can have very different Bn squares, can have very different variances. So they are still independent, but they don't share the same variance. That's it. Okay, then the central limit theorem here is about this thing, Zn over Bn. So Bn is the square root of Bn squared. So Bn is the variance and Bn is standard deviation. So essentially we have Zn divided by standard deviation. And we can show that as n goes to infinity, this thing, standardized Zn, goes to standard normal. And please note that here, the discussion, these are all scalar values, not vector values. So they are all scalar values. Okay. So what does this mean? So because there is a very strong correspondence between sum, Zn, and the row average, right? So you can think about this just as average. This is, sorry, Z2. This is just the average times 2. This is the average times 3. So essentially, each Zn is just the row average of size n. We can say that if we call that xn bar, is the row average times n. Okay, and we are dividing Zn by its own standard deviation. So it's the same as dividing xn bar by its standard deviation. Their standard deviation just differ by n. And then we're just saying that xn divided by standard deviation goes to standard normal. So it's the same conclusion, same result as central limit theorem. Nothing special. The statement is the same. So the conclusion is the same, but we need a different condition because here within the row, you may not have identically distributed random variables. That's the thing. The only thing we kept is independence and nothing beyond that. So we don't require the we don't require the identical distribution assumption. But there's no free lunch, right? To get the same central limit theorem result without identical distribution, you need to add some condition. And this condition is called Lindberg condition. And what does it mean? So remember, for the central limit theorem, what are the two conditions you need besides independence? The independence is 1. Independence is 1, or identically distributed is 1. I should say, we still keep independence, we drop identically distributed. Another thing we have is the finite covariance matrix, right? We need each random variable to be well behaved, not so heavy tail given its mean, right? That's always something we need. And here's the same thing. Essentially, you drop identical distribution, but you need also make sure that for each x and I, those here, we need them to be, how to say, quite concentrated around the mean. That's the thing. It's just that their means are now 0. Each x and I has mean 0. So the mean is 0. So we're looking at expectation of x and I squared, but we're only looking at the large values. The indicator of that x and I absolute value is greater than some epsilon times standard deviation. Standard deviation is the Zn standard deviation. And we take the sum across the i's within the row, within the nth row, I go from 1 to n. We take that and we divide this by the variance, Bn squared. So essentially, we want to say that the contribution of the large values of x and I to this x and I square, sum of them, this contribution is negligible given the total variance. That's basically what we mean. Because here, let me just say it, some clarification. Because x and I has mean 0, right? So therefore, we actually have the variance of x and I is just equal to expectation of x and I squared. We actually have that. And this is what we denoted as sigma and I squared. Okay, another fact is that the variance of Zn, which we denote as Bn squared, is just equal to the sum I from 1 to n variance of x and I, because Zn equals to sum of x and I, and x and i's are all independent. We still have independence. And then this is equal to sum I from 1 to n expectation of x and I squared. Okay, so what I want to say here is that Bn squared is equal to sum of x and I squared. But now we are not comparing Bn squared just to sum of x and I squared. We multiply this indicator function to x and I squared. In other words, we ignore the x and I squares that are within epsilon times Bn. For the small values, we just set them to 0. And only for the large values, we kept them here. All right. And we're just saying that the contribution by the large values of x and I is negligible within Bn squared. That's it. So in other words, the x and I values are not very heavy-tailed. They're not very far away from 0. That's what we mean. Essentially, this is the condition. Okay, so but I have to acknowledge that this is a technical condition. Yeah, this is a condition needed for the proof, and therefore it's formulated as this. Essentially, take-home message, random variables cannot be too heavy-tailed. They can, especially if they're shifted to have mean 0, they cannot be too far away from 0. Otherwise, we will violate the Lindberg condition and we will not have this central limit theorem like result. So Lindberg condition is a sufficient condition for this central limit theorem. Okay, I think that's basically it. That's the most important part for this theorem. The other way, conversely, is less interesting, I would say, because we go the other way around. We're saying that if we do have the central limit theorem like result, can we go to Lindberg condition the other way? Unfortunately, we cannot directly go there. We need to add an additional condition. That is, since Bn squared equals to sum of these sigma and I squared. Oh, sorry, you cannot see it. Bn squared equals this. It's just the row sums variance equals to the sum of the variances, right? So we just need to add another thing is that no single term's contribution to this total variance is significant. So as n goes to infinity, the contribution by a single one is negligible. So adding that, so no one term of the sum Bn squared plays a significant role in the limit. So adding this together with the central limit theorem like result, we get the Lindberg condition. Yeah, but I think this is less useful than the statement because we need to say that given the condition, we can prove central limit theorem like result. So in other words, if you want to derive central limit theorem for more complicated statistics, you try to formulate them in this type of triangular array. So you basically formulate, so this is like your sequence grows, right? Basically, you every row corresponds to one sample size. Given that sample size, you have n observations, but these n observations are not necessarily identically distributed. They're just independent. And then you look at the sequence average or sum, and then the standardized sum or average. By standardization, I mean dividing standard deviation, and also we have subtracting the mean to have mean 0. Then that will have limiting distribution of standard normal. That's it. Okay, so I'll show you some examples, some applications of Lindberg-Feller theorem to help you understand how we use it, essentially. If this seems to be a little bit abstract, that's fine, but we'll look at some applications.
Professor,
Yes.
I have a question. So here we're assuming units are independent, but like not identical. So by saying not identical, does it mean like we're even considering the case like unit by unit, they are generated from different functional forms?
Exactly.
Okay.
Different distributions. Exactly. Yeah. Yeah.
Okay.
And also, yeah, that reminds me of good clarification I should make. For central limit theorem, we only require IID, mean, the same mean, and the finite covariance, same mean, finite covariance matrix, but nothing about the distribution of x1, x2 to xm. They can come from any distribution, right? As long as they share the same mean and finite covariance. Nothing, but they're IID, yeah, so same distribution, but the distribution doesn't need to be Gaussian, but the sample mean turned out to be Gaussian. I think that's the magical thing about the central limit theorem, yeah. And here, same thing. Here, we drop the identical distribution, which means that they don't have to come from the same distribution family. And as long as they have mean 0, each mean 0, and identical, and independent, but they can have very different variances. But of course, their variances must be finite, right? And also, you need to have each random variable to be not so far away from 0. That's the intuition behind the Lindberg-Feller condition. Okay, so let me see. Yeah. Okay, let me look at the remark. This is something more important. In most practical applications of the Lindberg-Feller theorem, the Lindberg condition is used to establish asymptotic normality, which is this condition. Okay, Lindberg condition. Okay, let's read this. An important special case is created from a single sequence x1, x2 of IID random variables with mean, mu, and variance sigma squared. This is the setting of central limit theorem. But what we are doing here is if we define x and I as xi minus mu multiplied by its own z and I. So here the constant is different for everything. So that's why even you start from IID, but after this modification, x and i's are not IID because they have different z and I constants. Then we can use the Lindberg-Feller theorem to obtain the asymptotic normality of Zn over Bn, where Zn is this sum. Sum I from 1 to n, Z and I times xi minus mu. So you basically get into this more complex form of Zn, right? It's not just sum of xi minus mu, but we multiply Z and I for each xi. And therefore Bn squared, the variance of Zn will become this form, sigma squared plus sum I from 1 to n, Z and I squared. We can show that Zn over Bn go to this, provided this. And this is to satisfy the Lindberg condition. That is, in the sum of Zn I squared, yes, I think this is Zn I squared, the maximum of them, we call that max, and in the numerator, I just wrote j, okay, max j smaller than n, among all the z and j square, again, zn1 square to zn square, among n of them, we pick the max, and the max over the sum is negligible as n goes to infinity. So no single term dominates. No single term dominates the sum, Cn. Yeah, so essentially, this is another intuition I should say about the Lindberg-Feller theorem. Besides that, we need to have each random variable to be not so far away from 0. We also need that after the scaling in this special case, that no single random variable dominates in the total variance, right? So then I think this intuition makes sense because in the central limit theorem, the fact that you have the average behaving like normal like is because the average is not dominated by one particular random variable. If it is, then that particular random variable's distribution will dominate, right? And that distribution may not be normal, right? So I think you can just think about it from this perspective. Yeah, so we need some real average. Okay, and let's take a look to see why this satisfies the Lindbergh condition. We're just trying to show that the Lindbergh condition is satisfied by this condition. So recall that we need to show that this thing go down to 0, right? That's the Lindbergh condition. So essentially, here we just put in the formula of x and y. So what is x and y? X and y in this application is z and y times xi minus mu. So we just put this form inside, and then this is what we get. So this absolute value x and y greater or equal than epsilon times bn becomes xi minus mu greater or equal than epsilon times bn over z and I, right? That's what we have. And z and I squared goes here, outside of expectation because it's not random. Okay, and then we find the upper bound of it. The reason is because we need to introduce this maximum of z and I square or z and j square, I or j, doesn't matter, into our formula because we need to use this result. This is the condition we have, and we have to show that this implies the Lindbergh condition. So essentially, this greater than this, and this lower bound depends on I, right, for each I. But now we just replace the denominator by the maximum, j less or equal than n. So this is no longer specific to I. It's a general term. And you know, this term is bigger than this term, making this ratio smaller than this ratio, right? Because the larger the denominator, the smaller the ratio. And if the ratio is smaller, this indicator function is more likely to hold. Then you provide an upper bound of the previous one. Yeah. Okay, but the fact that this is nice is because now you introduce the max. And also, here, what we are doing here is, if you think about this bn squared, we are doing a replacement. We just replace bn squared by its form because in this special case, bn squared takes this form. We just put this form in. And then you can see that with this form in, another thing is we can actually now say, okay, here, this expectation is no longer specific to I. Why is that? The reason is because x1 to xn, they are IID. Okay, x1 to xn are IID in this setting. And now we change the lower bound in the indicator function to be a common one, not specific to I. Then essentially it's the same function applied to each xi. So x1, x1, x2, x2, no matter what we have here, since they are IID, then their expectation will be the same. That is another thing, right? So with this expectation, the same, staying the same for each I, we can get it out of the sum. That's why now here, expectation is out of the sum, and the sum here is only for z and I squared. Okay, and this z and I squared and this z and I squared in the bn squared can be canceled. Okay, and then we just have 1 over sigma squared. And for the expectation, we just use x1 as the representative because each xi is IID. We just have x1. All right, and now you see that we can use this fact that indicator function here can be written as 1 minus the indicator function of smaller than. We change the sign of the indicator from bigger or equal than to smaller, but that's 1 minus this, right? And then expectation of this term times 1 is just the variance of x1. And the minus term is here. Okay. All right. So finally, you see what happens here is that we are, okay, one more thing I forgot to say is that for the Bn here, we also, you see, here we introduce the definition of Bn here as well. Let me see if that's the thing, because we have Bn square or Bn. It seems that we put in Bn square here. I think there's something wrong with it. Yeah, because we need to put a square root here. But essentially the Bn also comes in here. So what I want to say here, ignore the square term because that's a typo, I think. What I want to say here is, given that you have, or we can square everything. We can square here and here, then that will hold. Anyway, what I will say here is that by introducing the max, by putting this expectation out of the sum is one thing. Another thing is that now we are closer to the condition here. It's max over the sum going down to 0. Okay, so if you follow this thing and go to this term, right? Indicator is less than, let's look at here. Essentially, the condition here will tell you that this term is going to what? It's going to infinity, right? Because we just reverse the inverse, the denominator and nominator. Before, in the condition, we have max over sum going down to 0. And here we have in this upper bound, in the indicator function, is sum over maximum. So this will go to infinity. And this going to infinity means what? Means that the indicator function is going to 1. Because the upper bound is infinity, then the indicator function will always hold. Okay? So therefore, this function will basically, this expectation will basically converge to just expectation of x1 minus mu squared. And that's the variance. So essentially we have variance minus variance 0. That's how we show the Lindbergh condition. Or if you just want to stop here without going down, if you just want to stop above the line here, this is also obvious. So without going down to the detailed argument, we can see from here, this is also sum over max, right? As we said, this is going to infinity. And if this is going to infinity, then there's no possibility for this x1 minus mu to be greater than infinity. So this indicator function will go to 0. And that will make this left-hand side go down to 0. So it's just to check the Lindberg-Feller condition. But the intuition here is that if no single term dominates, then the condition actually here it holds. Does that make sense? So for this, maybe for the special case, it's easier to understand than the general Lindbergh condition. So essentially here, we introduce the z and I here because that's how we define x and I, right? We go to here and then we get a z and I out. And here we want to have a term that is not specific to any I. So that's why we take the max here. And then we can just go into this ratio, which is the inverse of what we have in the condition. Okay. So Lindbergh-Feller theorem essentially is to show this term going down to 0 as n goes to infinity. If you have that, then you have the central limit theorem-like result. That is, Zn over Bn converges to standard normal. And in this application, you can see Zn is not just the sum of xi minus mu, but they can each be scaled by Zni. And this condition is regarding the coefficients Zni. They must be behave in a way that no single Zni dominates. That's it. Okay, sorry. Actually, I think some, can you hold on for 1 minute? Okay, so for this part, do we have any questions? Or do you need any more explanation besides the technical part? And I can show another example to help explain this Lindberg-Feller. Yeah, previously, before in previous years, we had homework, so you should be able to do some practice yourself. But this year, I will rely on yourselves to see, yeah, you can try to see, work on this example. Like I said, there's a typo here, we need to correct that. Just try to correct that yourself and see how the proof can go through. Okay, so let's continue. Okay, so there's a stronger result we could use in practice. And this is called the Lyapunov condition. So this condition is stronger than Lindbergh condition, but it's simpler in the form. So if you can show this instead, then this implies Lindbergh condition, and that Lindbergh condition implies the central limit theorem result. So you can prove this instead. So essentially, it's just that you want to find one single delta, positive delta, such that this thing holds. What is this? So remember how we define Bn squared again, right? So Bn squared is the variance of Zn, and is the partial sum Zn is the variance of sum of x and I. I goes from 1 to n. This is Bn squared. So we know that if you just have Bn squared, let's look at here. 1 over Bn squared, sum of expectation of bracket x and I squared. Or in this case, I can put absolute value, doesn't matter because it's square. I from 1 to n. Right. This is what? This is equal to 1. This is what we know by definition. Because x and I squared has mean 0. So expectation of x and I squared is just the variance of x and I. That's it. But now you raise the power of both. You change both from 2 to something more. 2 plus a positive delta. By increasing this, if you can show that this go down to 0 as n goes to infinity, then this implies the Lindbergh condition. Okay, why is that? Let's look at the proof. Actually, the proof is surprisingly one line only. So let's look at it. Assume that the Lyapunov condition is satisfied and fix epsilon greater than 0. This is the epsilon we needed in Lindbergh. Since x and I greater or equal than epsilon times Bn implies what? Implies that x and I over epsilon Bn, this is a ratio greater than 1. We raise it to a positive power delta. It stays greater or equal than 1, right? There's no problem that. Then, in this Lindbergh condition, see here, now you basically multiply this term, okay? Epsilon power delta, epsilon power sigma, Bn power sigma, they go to the denominator. And x and I power delta go to the numerator. So you just multiply into that. Because this is greater or equal than 1, the multiplication give you an upper bound. Greater or equal than this. You basically multiply this ratio here. Okay, this indicator stays. But you only care about when the indicator function takes value 1. Because if it takes value 0, you don't care, right? For the value 1, it implies that this holds. Right, so essentially you can always go here. So you go from here to here because when the indicator function holds, then this is an upper bound. And you can further drop the indicator because the indicator function is either 0 or 1. You just set it to 1. And that's what you get out here. And then you can see if the right-hand side goes down to 0, then the left-hand side goes down to 0. Does that make sense? So essentially just find the upper bound of it. Yeah, that's it. That's basically it. And so in this case, but you can also see why I cannot drop this indicator just from here. Just to think about another way, right? You say indicator can always be bounded by 1. Why can't I just set this to 1? Because in this case, you get into what I have the equation here. If it's just square here, it's 1. So this upper bound is not useful. This upper bound is 1, stays as 1. You cannot go down to 0. But here, by multiplying this delta power to each term, then over here, you are not getting a value of 1. You can let this go down to 0. You can change this to go down to 0, and this will imply this to go down to 0. So essentially, you can make the upper bound go down to 0. So what does this imply intuitively? It implies that if you have a power greater than 2, then the increase in this sum, in the sum of expectation here, is not as fast as the increase in the denominator. The denominator increases faster. Because here, the bn squared is like the sum of this, right? So essentially, let me say it another way. Maybe you can make it more straightforward. If we look at the ratio, the numerator is I go from 1 to n, expectation, x and I raised to the power 2 plus delta. All right. And the denominator is what? The denominator is this. Let me think how to write it. It's actually square root of sum I from 1 to n, expectation of x and I to the power 2, square root to the power 2 plus delta. This is it, right? Because under the square root, that's our, and the square root is our bn, basically. So we're saying that this increase is slower than this increase. The denominator increased faster. So that's why this go down to 0. And again, this implies that no single term in the sum actually dominates. That's another implication of that. Okay, so this is a Lyapunov condition. Now let's look at some more concrete examples, less abstract, to help you do the application. Example 1, suppose that we perform a series of independent Bernoulli trials with possibly different success probabilities. Okay, so we have the coin tossing, independent Bernoulli trials, but each toss has a different chance of getting ahead. Under what conditions will the proportion of successes properly standardized tend to a normal distribution? That's our question. Okay, proportion of successes properly standardized tend to a normal distribution. And here it is. So let xn follows Bernoulli Pn. Okay, n goes up, right? And the Pn can be different. So we just want to create a scenario where each random variable has mean 0, because that's what the Lindberg-Feller theorem requires. So that's why we define yn to be xn minus Pn. And we also calculate sigma n squared as the variance of yn. It is also the variance of xn. We know it's Pn times 1 minus Pn, right? This is a well-known result from Bernoulli. Okay, use the Lindberg-Feller theorem. Let us check the Lyapunov condition. Now let's check the one simpler to check. Say delta equals 1, because we can have that for any, as long as we have one delta. So we check delta equals 1 because that gives us a cube, right? Cubic, that's easier. Verify that expectation of yn cubic. So what do we want to verify? It's this one. We want to verify this. Okay. And yn, expectation of yn cubic is Pn plus 1 minus Pn cubic. And this is just following the definition of expectation, nothing special. So essentially, yn can take only 2 values. So yn is equal to minus Pn right? When x take value 0, so with probability 1 minus Pn, or Yn takes value 1 minus Pn with probability Pn. That's it. So with this result, we just write out the expectation of Yn cube in this form. It's just a definition of expectation, nothing special. And now, given this form, we put in sigma n squared for replacement, and this is what we get. And we can easily show that this is bounded by sigma n squared. Because this one minus this one, we know this is for sure less or equal than 1. So we know that. All right, so essentially, now you take the sum across I from 1 to n, right? You have the partial sum here. Even though here your triangular array is a little bit more specific, simpler than the general form, because here you just have y1, y1, y2, y1, y2, y3, y1, y2, y3, y4, so and so on. So every row is a sequence, you take the partial sum, but here every row share the entries. And that's the special case of the Lindberg-Feller theorem. But that is the general form is more general than this. So we have this under Bn squared. Okay, so therefore, the Lyapunov condition is satisfied whenever Bn squared, which is an upper bound on this, over Bn cube is going down to 0. That is Bn must go to infinity. And what is Bn? Bn is this. Let me see. Bn should be this. Bn squared is a typo. So Bn squared is the sum of sigma I squared, I from 1 to n, is this. So as long as we can have this go to infinity, it is sufficient to say that the Lyapunov condition holds. Then it is sufficient to say that we still have the central limit theorem like result. Okay, essentially, we still can say that the Yn after standardization goes, Yn after standardization I should say the sum of Yn, the partial sum, y1 to Yn, partial sum after standardization converges to a normal distribution. And to satisfy this sum as I go from 1 to n goes to infinity, diverge, going to infinity, we have to say that Pn times 1 plus Pn does not tend to 0 too fast. Otherwise, you wouldn't have a divergent sum. Does that make sense? So if you think about the IID case, all PIs are equal, then you can see for sure this will diverge, right? Because you have n copies of the same thing adding together. As n goes up, this goes up. So in other words, you need this to hold intuitively that as you toss your coin, the success probability shouldn't go down to 0 too fast. Otherwise, you would have no central limit theorem. Because in other words, how to say it? In other words, if you think you keep tossing, right? Tossing many, many times, but if the success probability go down to 0 too fast, essentially you will for sure or go down to 0 too fast or go up to 1 too fast, either way, because you want this product to be not going down to 0 too fast. So in other words, if it's going down to 0 too fast or going up to 1 too fast, it means that you will almost surely getting ahead or a head or a tail for sure. So there's no more randomness in the coin tossing. And then your average will only be based on the first few of your tosses. So essentially you are far away from the central limit theorem, where you need a lot of repetitions in your random events for average. Yeah, that will be my intuition for interpreting this result. Yeah, so you hope that even though you are no longer under identical distribution, but you are still similar to what you get under the standard central limit theorem. That's what we hope to have. Okay, any questions regarding this result? Okay, so if no more comment, let's look at another example. So example 2 here. So what we just showed is called example 1. Extension of example 2. Now let's look at binomial. Not Bernoulli, but binomial. So we have this n here. Zn is binomial npn. We would like to show that for this Zn also a partial sum, right? So essentially in every row, because we can now write this as, if we write this triangle, here is x11, x21, x22, x31, x32, x33. So still, and we can say that every row has its own p, right? P1, P2, P3. So they share the same P. And we have n of those in the nth row, and Zn is the sum. That's it. So essentially, we want to show the partial sum follows the central limit theorem result. So again, we can show that in this case, this npn1 minus pn is the variance of Zn. So let's say the expectation of Zn is just n times pn based on the binomial. Variance of Zn is n times pn times 1 minus pn. Okay, so as long as the variance is going to infinity, then we have this result. And you can see that this is basically consistent with the intuition we just gave you, because it means that you still need to have the, how to say, as your n goes up, right? You still need to have the row sum or the partial sum Zn to have increase in variance. That is, the more tosses you have, the more randomness you have. So then you are like the central limit theorem setting where you have IID. Because if you do have IID, then Pn is fixed, right? And then for Pn fixed, then n times p times 1 minus p will for sure diverge. You want to still be like that. Okay, so here, let's look at xn1 to xnn. So here we just introduce Pn here to make sure xni has mean 0, nothing else. We just want to create a mean 0 scenario for Lindberg-Feller. So therefore, xni is equal to the Bernoulli minus Pn. And then sum of x and i will become Zn minus n times Pn, which is our denominator here. So x and i has mean 0. Variance of x and i is Pn times 1 minus Pn. And the Bn squared in the Lindberg-Feller theorem is the variance of the sum is n times Pn times 1 minus Pn. Okay, so we are left to check Lindbergh condition. For any epsilon greater than 0, this is Bn squared, okay? And this is the sum x and i, and this is the standard Lindbergh condition. X and i absolute value greater than epsilon times Bn, and Bn is the square root of Bn squared, going down to 0. Okay, since x and i in this case is less than 1, that's because of here. That's because of here. So x and i is equal to this Bernoulli Pn. This is between 0, either 0 or 1 minus Pn. So that's why, you know, this x and i's absolute value must be bounded by 1, right? Because it cannot go below -1, cannot go above 1. So therefore, this indicator function will be exactly 0 whenever this term is greater than 1. So this indicator condition no longer holds, never holds, is 0. So to make this greater than 1, a sufficient condition is to let this diverge, right? When this diverge, then for any epsilon, you will find a corresponding n such that their product is greater than 1. And then when this is greater than 1, indicator doesn't hold, then this will become 0. So that's how we can show it. Yeah. This is a necessary condition. Okay, so this is second application of Lindberg-Feller to show that if you have the coin tossing changing, then you can still have central limit theorem like result, as long as your coin tossing probability doesn't converge to 0 or 1 too quickly. Last example, it's about linear regression. Application to the asymptotic normality of the least square estimates of a regression coefficient. I know many of you here are, actually all of you here are in my previous class 205. So you should have seen this linear regression, right? So suppose that, and this is simpler than what we did because it's simple linear regression, only one predictor. So yi is equal to alpha intercept plus beta slope times xi plus epsilon I error term. So when the xi's are known and not all equal, and epsilon or IID with mean 0, finite variance that are same, we can show that given this xj minus xn bar average square over the sum, so the maximum over j. Again, it's that in this sum of xi minus x bar square, no single term dominates. So the max term over the sum go down to 0 as n goes to infinity. Then this beta n hat, which is the coefficient least square estimate for beta, this will follow central limit theorem. Yeah, so this is more important because essentially, I remember in 205, we give you the asymptotic result in it directly. We didn't prove that. But now you can see that to prove that, you can just use Lindberg-Feller theorem. So in this case, beta n hat can be considered as somewhat weighted sum of yi, right? But your weights are different for different I. Okay. So essentially, we are having yi times xi minus xm bar. Okay, this is the sum divided by the sum of xi minus xm bar squared. So it's a sum over sum, but yi is involved in the numerator. Okay, so how do we prove it? This is asymptotic normal. So note that this is our Bn hat. It's this, and we can actually use the fact that, okay, we can have yi equals to alpha plus beta xi plus epsilon I. This is the model. We just replace yi by the right-hand side, so beta can get in, and we can have beta here, and then we have epsilon I left here. Okay, and we will show that the Lindbergh condition is satisfied with this x and I defined this way. So now you can see why we have the sub-index ni, because we need to involve the sample size, and we also need to involve the ith observation in the sample. So epsilon I times xi minus xn, and it's actually coming from the numerator here, our definition of x and I. And also we need this x and I to have mean 0 in the Lindbergh-Feller theorem. That's why we construct it this way. So it does have mean 0, and it has variance in this way because epsilon I has variance sigma squared. Let me just write it here. Okay, so then the Bn squared is the sum of variance and ni would just be sigma squared sum. Okay, now let's check the Lindbergh condition. That is this. And we just replace x and I by this term. Do the replacement here and here. Okay, and upper bound. You see, we use the same technique as we use in the first example of Lindbergh-Feller. Before example 1, the example we introduced right after the theorem. That is, here you have in this indicator, right? This indicator is just, let me just write it. Epsilon I greater or equal than epsilon Bn over absolute value xi minus xm bar. This is what we have. And now we replace the denominator by the max. Same technique as we used, right? This is for I. And now we replace by any j maximum. So the maximum of j going from 1 to n. So the reason for doing that is, again, now this denominator has nothing to do with I. And now we can use the fact that epsilon i's are IID. So they have the same expectation. That's why. Okay, so now we introduce this max over sum. We call that gamma n. Okay, and because Bn here involves sum, right? So that's why Bn is sum, and here we have the max. So that's why you can replace this ratio by gamma. Basically, gamma can be introduced here. You're left with delta sigma over gamma m. And if this is not so straightforward to you, just try to do some algebra here and you will see that's it. This is gamma m. So as I said, epsilon i's are IID. This is the fact we used before. So now the overbounding indicator function is not specific to I. Then we can replace epsilon I by any epsilon 1. So we can just use epsilon 1. And then we can get this expectation out of the sum. Okay? Then we just have sum of xi minus xn bar squared. We also have the sum, same sum in bn squared. So we have cancellation. Yeah, this is very, very similar to the first example. Then 1 over sigma squared and expectation. Okay? And okay, so the condition says that no single term's square difference from the average dominates the term. Then gamma squared goes down to 0 as n go to infinity. So this holds. This is our condition. So this holds. So then basically Lindbergh condition holds. Yeah, that's what I'm going to say. So Lindbergh condition holds. Then we have asymptotic normality for Zn. All right. And here just want to say that Zn is this. So Zn is this part. So we have asymptotic normality for this part, and then we can have asymptotic normality for beta n hat. That follows. So I know that I'm going quite fast on this part. So this is what we get for the Zn part, and this is what we get for beta n part. But I really hope that if I want to study one example in detail, this should be it, because this is the most important application of the Lindberg-Feller theorem to the linear regression setting. Okay, and then you can see why we can show asymptotic normality. And another way to show it is to go through the maximum likelihood estimation theory, to do the MLE theory, because we can prove in general that MLE is asymptotically normal, then beta n hat is also MLE, and that route can also go through. But for beta n hat to be MLE, we actually need a stronger assumption. What is that? The stronger assumption for that is that we need to assume epsilon i's to be normal. They must be mean, 0, sigma square, and normally distributed. That's where we can get that least square estimator is MLE. So that's more assumption. But for this route, going through just least square without assuming epsilon I to be normal, they can be any distribution, just finite variance and mean 0. This is more general, and this requires the Lindberg-Feller. I hope that makes sense to you. Yeah. Okay. All right, so I think we were going really fast today. So I know. So we have covered many, many things. So maybe, probably, I will just quickly say a little bit about this next extension to begin it, and then we will continue next week. So for those of you who really want to get something out of this class, as I said, unfortunately, without a reader this year, we lack the exercise practice, but I still hope that you can try to at least look at the notes to fill in the details and try to do some algebra, right, to help you familiarize with it. The Lindberg-Feller theorem is the most important thing for this part. Okay, for next part, which we'll just begin a little bit, is the stationary M-dependent sequences. What does that mean? So here, let's say IID, right? IID means independent and identically distributed. Okay, for Lindbergh, we drop identically distributed, we keep independent. Here, we drop independent, we keep identically distributed. So we are in the other scenario where we do have identically distributed random variables, but they are no longer independent. Okay, that's challenging, right? If they can have any dependence, it doesn't work. For example, I can give you one extreme scenario, that is all my random variables are identical. Okay, when that is the case, perfect dependence, then having n observations
is essentially having one observation. The sample size n doesn't matter. They're all equal. In that case, central limit theorem will for sure break down, right? So you can think about that. So right now we drop independence, but we're imposing a specific dependent structure called M dependent, which means that any dependence only happen within the range of M. Beyond M, they are still independent. So this is kind of like weak dependence, right? Dependence is only to a degree. Okay. So therefore, to explain this, we will introduce this concept called stationary sequence. So the sequence x1, x2 is said to be stationary if for any fixed k greater than 0, the joint distribution of xi to xi plus k. So you have k of them here, right? Actually, k plus 1 of them. Yeah, k plus 1 of them. xi plus 1, right? So k plus 1 of them is the same no matter where integer I is chosen. So in other words, you have a sequence. I can start from anywhere. Like look at the sequence of k plus 1. And then you say that sequence, the subsequence, have the same joint distribution. This is what we call stationarity. And this is quite important in some time series problems, right? So you don't care where you start. Whenever you start, but the joint distribution stays the same. Okay, so under stationarity, covariance of xi and xj depends only on the gap j minus I. That is, covariance x1, x4 is the same as covariance x2, x5, same as covariance x3, x6, and so on. So their gap matters, but not the position. Okay. And this is something important regarding the variance of x and bar, because you know in this case, it's no longer just sigma squared over n because you have dependence. And this variance x and bar, let me just write it, equals sigma squared over n is only under independence. Independence and same variance, right? Same variance. Otherwise, if you have dependence, it's not like this. So therefore, you see, for the variance x and bar, we need to consider covariances, right, between each two. This is just the general formula. But one thing to know here is, since it's stationary, then stationary can come in here to make it not so complicated. What does it mean? Because you know, for here you look at all pairs, right? But we can just say that we just look at I less than j. Because when I is equal to j, it goes here already. When I is equal to j is the variance, it's here. And this covariance is only for I doesn't equal to j. But since we have symmetry, right, for covariance, like covariance of xi, xj is equal to covariance of xj, xi. So we can force I to be less than j, and we multiply that by 2. That's it. Okay, and then from here, since we know that x1, x4, x2, x5, they have the same covariance because of the stationarity. That's why we can just enumerate the gap. You can consider all possible gaps between x and xj. Smallest gap, 1. Biggest gap, n minus 1. And for each gap, we just calculate the covariance. And we consider how many pairs have this gap. If the gap is 1, we have n minus 1 pairs. If the gap is n minus 1, we have just 1 pair, right? So that's how we do the enumeration. This is how we express it. But this can give us a simpler formula, because we can just say that for gap k, we call this covariance gamma k. Then we can just have this replaced by gamma k, and this is the formula we get. So essentially, we can say that variance of x and bar is just equal to, let me just write one more step. X and bar is just equal to sigma squared over n plus 2 over n squared sum k from 1 to n minus 1, n minus k gamma k. That's it. That's the variance of x and bar. And now we go into the variance of root n times xn bar minus mu. This is the mean, right? They'll scale this by root n. So we should multiply n to each term here, right? And then sigma squares here. And this 2 over n squared becomes 2 over n. And the sum stays. So this gives us the formula here. All right, but the right-hand side still involves n in the second term. So you see, in the sum, k goes from 1 to n minus 1. So n minus 1 terms here, and we divide the sum by n. So if we can say this has this, if it has a limit, then we can say that, okay, in the limiting distribution, the variance becomes sigma squared plus the limit, the gamma. So we no longer involve n, because n should be gone, right? I said in the limiting distribution, we shouldn't have n should only stay on the left-hand side. Does that make sense to you? This whole derivation, right? We are just talking about stationary sequence. So this is what we have for stationary sequences. Yeah, the limiting distribution for stationary sequences, not beyond anything like that. But now we are saying that this only holds when we have this limit. If this doesn't converge, then we don't have the result. Okay, if this converges to, if this diverges, then the variance will explode. So you won't have the result. Okay, so yeah, maybe last thing before we end today's class is the M-dependent sequence. I'll revisit again, so don't worry too much. So for M-dependent sequence is something I just said. So essentially, if your two subsequences have gap larger than M, then they are independent. So as long as the gap is bigger than M, they are independent. So M-dependent sequence is just kind of weak dependence. All right, yeah, so last time we'll come back to revisit the concept again. So two extensions of CLT. One is to drop identical distribution. The second is to drop independence. And we have some more general result. Hopefully, yeah, hopefully it's interesting. And as I recorded a lecture, right, if you need to slow down a little bit to go over the concepts or read the notes, I have posted notes to our announcement like last week, so you can check it out there. Then if you have any questions, I welcome them in our next lecture. So yeah, I'll see you in person next Monday.
Thank you.
Thank
Thank
you.
you.
Thank you.